Okay, prepare the notes for section 6.8. This is about evaluating definite integrals when there's u-substitution involved. So we already have some practice now evaluating antiderivatives when there's u-substitution. And now we're going to see how that works when we're using the fundamental theorem of calculus part 2 to evaluate a definite integral. Similar to your notes for u-substitution, the best way I think to do this is just to jump right in with some examples. So, without further ado, here's an example. Let's see if we can evaluate. So, you might have seen a problem like this in recent homework, right? We can do that using a u-substitution. But now we're going to have limits of integration here. So now, if you wanted to, you could think of this as an area, the area from 0 to 2 under this. We suspect that this is going to involve u-substitution because there are two pieces here, right? It looks like something popped out, and it looks like this looks like the what's inside. So I'm going to go ahead and try to make u to equal x squared plus 1, and then du would be equal to 2x dx. And there's the x that I need with the dx. And I don't have the 2, so I'm going to go ahead and put a 2 in here that I need, which means that I have to balance that with a 1/2 on the outside. All right? So far this is nothing new. So now I make the substitution, 1/2 the integral, and I'm going to pause for a minute. I'm not going to write the numbers down here yet. I'll talk about that in a second. And looks like here we have u cubed, and then du is 2x dx, which I've got there. Okay, now there's two ways to do this. You can go ahead and evaluate this and then plug the x, like replace the u with the x squared plus 1 and use the original 0 to 2. But there's a better way, and I'm really going to try to sell you on the better way. Since we know that u is equal to x squared plus 1, if I can change these to u numbers, then it's going to be much easier. We're going to be able to get to the solution faster. We never have to turn back and go back to x's. So if x is 0, then u would be 0 squared plus 1. So my new number down here, now that I've gone over to u's, will be a 1. Again, that comes from taking this, which is an x number, right, an x value, plugging it in here. That gives me a 1. Likewise, if I plug in 2 in here, 2 squared plus 1 is 5. Okay? So this original integral that we started with is the same as this one. It will have the same value, right? Because we've transformed our x values here into u values. And now, that's 1/2 times, take the antiderivative of u cubed, which is u to the 4th over 4, from 1 to 5. Now, I don't know about you, but I don't know about you. I do know about this u. I don't know about you personally, but my preference is if there's any multiple, any kind of, whether it's a fraction or a constant multiple, whatever, I like to take that to the outside first, so I'm going to do that. I'm going to bring that 4 to the outside and make that 1/8 times u to the 4th from 1 to 5. Okay? If it seems like if you're not sure why you would be able to do that, you think about when you plug these in, you'd just be able to factor out the over 4 that's going to show up in both terms. So that's all. I'm just doing it now. I think it's a little easier that way. So that's 1/8 times 5 to the 4th minus 1 to the 4th. 1/8 times 5 to the 4th, 625, as you know, I'm sure, minus 1. And it looks like I'm running out of room on the screen there, so I'll go down here. So that's 624 over 8. And I think those are both divisible by 4, it looks like. 600 divided by 4 is 150, so 156. Oh, maybe they're both divisible by 8. 156, so 78, I think. You can check that, but I think that's equal to 78. So there you go. So again, recapping here. We found the antiderivative, right? But instead of, at this point, if we were just finding the antiderivative, I would have at this point gone back and plugged the x squared plus 1 back in here. But because it's a definite integral, I can just swap these numbers for u values, right? Using what I chose for the u, and then evaluate the integral that way, and we never have to look back. If you do change it back and plug in the 0 and the 2 for the x values, you will get the same thing. It's up to you how you want to do that, but I'm going to really try to sell you on this method, and I think whatever you choose to do, we should do it consistently. So why don't we all do it the way that I like best? All right, let's try some other examples. How about this? It's the integral from 0 to pi over 8 sine to the 5th 2x times the cosine of 2x dx. And again, I'm just going to take a second to rewrite that in the notation that we like better. That really means sine of 2x to the 5th times cosine of 2x. I think that helps us see a little bit that a little bit better, maybe that is the what's inside. So u is equal to sine of 2x. Du is equal to 2 cosine of 2x. And that is the cosine of 2x that we need. Right? That 2 popped out because of the chain rule. Okay? Now, I need a 2. So I'm going to go ahead and put the 2 in there that I need. You can stick it right there. I mean, if you want to put it right there, so you can see the 2 cosine 2x. That's fine too. And then that's fine 2. And then need a 1/2 there for balance. Okay. Now we're ready to make our substitution. So we have 1/2 times the integral. I'm not going to write down those numbers yet. I'm going to come back and do that in a minute. I'm going to focus on this first. This would be u to the 5th, and then the 2 cosine 2x. Sorry, I should write it. I should have done that at this stage, right? Let me do those here. There's my 2 and my 1/2. And then there's the 2 cosine 2x dx. 2 cosine 2x dx. Sorry, I forgot to write that down. That's du. Okay, now what would my new numbers be here? Let's see, if I plug 0 in here, that's the sine of 2 times 0, the sine of 0, which is 0. If I plug in pi over 8, that would be the sine of 2 times pi over 8, or pi over 4. That's the square root of 2 over 2. Right? So it's 1/2 times the antiderivative of u to the 5th is u to the 6th over 6 from 0 to the square root of 2 over 2. I'm going to take that 6 to the outside. That 1/12 times u to the 6th and the square root of 2 over 2 is 0. That's 1/12 times square root of 2 over 2 the 6th minus 0 to the 6th. Right? And then this is a little bit of, I suppose, Algebra 1 or something when you learn how to do this. Maybe Algebra 1 Advanced. I'm going to raise this fraction to the 6th power. I have to do that to the top and the bottom. Well, the bottom's easy. 2 to the 6th is 64. The square root of 2 to the 6th, well, the square root of 2 squared would be a 2, and then I get 3 of those. So the square root of 2, and you can pause and think about that for a minute, but the square root of 2 to the 6th is the same as 2 cubed. That's 8. And let's see, 8 over 64 is 1 over 8. It's 1/12, so that's 1 over 96. There you go. There's another example. Now let's see, I'll do at least one more. How about, I think I see 2 more examples in front of me here that we can do. I'm pulling these examples from the book. These are just the examples at the beginning of section 6-8, or some of them at least. So let's try this. So the integral from 0 to 3/4 of 1 over 1 minus x dx. Okay. So let's see. What's the u here? Well, that looks like it wants to maybe be a natural log thing, so I'm going to try. I mean, just making u equal to x isn't going to work, so maybe we can try this. U equals 1 minus x. And du would be equal to, derivative of that would be negative dx. All right, so it looks like I just need a negative sign in here. So I'll put a -1 here, and a -1 out here to balance that. And I can make my substitution. So I have negative. You can put a -1 there. You can just put a negative sign, same difference. I'm going to leave these off for now. And it's 1 over u, -1 dx, that's what I needed there, du. And my new u numbers, 1 minus 0 is 1, and 3/4, let's see, 1 minus 3/4 would be 1/4. Okay, so the negative sign there. Then the antiderivative of 1 over u is natural log. And here it's actually really important to put the absolute value signs in. Not in this particular problem because it's those are both positive. But if these are negative, you need that. Otherwise, you're going to be trying to take the natural log of a negative number. And can you do that? Okay, so that's from 1 to 1/4. So that's a negative sign. And I have the natural log of 1/4 minus the natural log of 1. And of course the natural log of 1 is 0, so that's negative natural log of 1/4. Now that's a version of the correct answer, but probably if it was a multiple choice kind of scenario, that's not going to be the answer that's there. Remember that per our logarithm rules, we can bring that in as an exponent. That's the same as the natural log of 1/4 to the -1, and 1/4 to the -1 is 4. That's, I think, arguably a better looking version of the answer than that is. All right. And one last example. Now let's see, how about integral from 0 to the natural log of 3 of e to the x times 1 plus e to the x to the 1/2 dx. Well, this is one of those problems with parentheses, so it looks like I think that probably is wanting to be the what's inside. So I'll take a shot at that, see if it works. So let u equal 1 plus e to the x. The derivative of that, derivative of 1 is 0, derivative of e to the x is e to the x dx. And hey, look, there's my e to the x dx. So I don't have to insert any numbers here. I have exactly what I need. So let's see. That's now going to look like the integral. I'm going to wait, not write down those numbers yet, of, this is u to the 1/2 du, right? And then plugging 0 in here, that gives me 1 plus e to the 0. E to the 0 is 1, so that new number is going to be 2 here. And then plugging the natural log 3 in, e to the natural log of 3 is 3, so 1 plus 3 is 4. Right? You can tell anybody who's interested in listening that you learned in calculus today that 1 plus 3 is 4. And the antiderivative of that is the new exponent, bump that up 1 is 3/2, and then that'll be multiplied by 2/3, which I'm just going to go ahead and put right on the outside there, from 2 to 4. That's equal to 2/3 times, let me write this out, alright, what's 4 to the 3/2? Well, this means square root. The square root of 4 is 2, cubed is 8. The square root of 2 is the square root of 2, and then cubed is the square root of 2 times itself 3 times. Well, 2 of those make a 2, so that's that. You can maybe pause for a minute and think about that. Make sure you're on board there. And I don't think there's a whole heck of a lot of simplifying that I can do here, meaningful simplifying, but if you wanted to, I guess you could say that's 16/3 minus 4 square roots of 2 over 3. You can put it all over a 3 if you want, whatever makes you happy. Right? And there you go. That's how this game works. Take some practice, I think. You have to make sure that you learn to hold off on writing those new numbers down. The temptation might be to immediately copy down these, right? But once you go over to the u's, as soon as you write down these u's here, you cannot write down these numbers anymore, right? You can't write down the old x numbers. You've got to either leave them blank for the moment or immediately change them over to the u numbers. And that's all she wrote.